The transformation of remote Pacific islands into operational airbases within days of their capture ranks among World War II's most remarkable engineering achievements. The U.S. Navy construction battalions, universally known as the Seabees, accomplished this feat through innovative use of two materials that revolutionized military construction: pierced steel planking and crushed coral. This combination solved what had seemed an insurmountable challenge: how to build airfields capable of handling 70-ton bombers on tropical islands that possessed neither suitable soil nor conventional construction materials. When Japan attacked Pearl Harbor on December 7, 1941, and subsequently swept across the western Pacific, American military planners immediately recognized that reclaiming this vast oceanic theater would require a network of forward air bases. The distances involved were staggering. From Hawaii to the Philippines stretched over 5,000 miles of ocean, dotted with thousands of islands, most small, remote, and undeveloped. Traditional naval power alone couldn't project sufficient force across such expanses. Land-based aircraft were essential for reconnaissance, air superiority, close air support for amphibious operations, and strategic bombing of Japanese positions. Yet constructing airfields presented seemingly impossible challenges. A runway for heavy bombers required at least 5,000 to 6,000 feet of length and had to support aircraft weighing up to 70 tons when fully loaded with fuel and ordnance. Conventional airfield construction in the continental United States took 6 months to a year, required massive quantities of gravel and crushed rock for foundations, and used either concrete or asphalt for surfaces. None of these materials existed in usable quantities on Pacific islands. The coral atolls and volcanic islands that comprised potential base locations offered no natural aggregate. Their soils, when present at all, consisted of either volcanic ash that turned to sticky mud in tropical rains or beach sand that couldn't support any significant weight. Shipping conventional construction materials across the Pacific was logistically impossible. A single concrete runway consumed thousands of tons of cement, aggregate, and reinforcing steel. Cargo ships capable of transporting such quantities were desperately needed for fuel, ammunition, food, and other combat supplies. Moreover, even if materials could be shipped, conventional construction timeframes were unacceptable. The island-hopping campaign strategy required American forces to capture an island, establish air superiority from that base, then use that air coverage to support the next amphibious assault. Any delay in making captured airfields operational would stall the entire offensive. The solution emerged from an unlikely combination: an innovative steel matting system developed by American industry and a building material that literally lay beneath the feet of every Marine who waded ashore: coral. Pierced steel planking originated not from military engineers, but from civilian industry responding to Army Air Corps requirements in 1940-1941. As the United States prepared for potential war, military planners recognized that rapid airfield construction would be crucial. The Army needed a portable runway surface that could be quickly laid over unprepared ground, didn't require specialized installation equipment, and could support heavy aircraft. The Carnegie Illinois Steel Corporation, a subsidiary of U.S. Steel, developed the winning design in 1941. Their engineers created interlocking steel planks measuring 10 feet long and 15 inches wide. Each plank was stamped from steel plate and featured circular perforations across its entire surface, hence the name pierced steel planking. The perforations served multiple purposes. They reduced weight from what would have been 90 pounds per plank to a more manageable 66 pounds. They allowed rainwater to drain through the surface rather than pooling, and they provided tire traction similar to a perforated metal walkway. The true innovation lay in the interlocking mechanism. Each plank's long edges featured different profiles. One edge had protruding hooks while the opposite edge had corresponding slots. When laid side by side, planks hooked together, creating a continuous surface that distributed loads across multiple planks. End connections used a different interlocking system, allowing rows to connect longitudinally. The entire system required no tools, no fasteners, and no specialized skills. Two men could lift and position a plank, hook it to its neighbors, and move to the next one. A trained crew could lay hundreds of linear feet per day. The engineering principles were sound. Aircraft wheels concentrated enormous loads onto small contact areas. On soft ground, these concentrated loads caused wheels to sink. The interlocking mat system distributed each wheel load across dozens of planks, which in turn spread the force over a much larger ground area. This load distribution meant that PSB could function on foundations that would otherwise be inadequate. Ground that couldn't support a 70-ton bomber directly could support the same aircraft when a PSB mat distributed the load. Initial tests occurred at Marston, North Carolina in early 1942, giving the matting its common name, Marston mat. Army engineers laid PSB over soft Carolina clay and subjected it to repeated passes by heavy bombers. The results exceeded expectations. Not only did the mat support aircraft weight, but it also proved remarkably durable. Hundreds of takeoffs and landings caused minimal damage. Damaged planks could be quickly unhooked and replaced without disrupting the entire runway. Production ramped up rapidly in 1942. Steel mills across America retooled to produce PSB. The War Production Board allocated steel specifically for matting production, recognizing its strategic importance. By mid-1942, monthly production exceeded 50,000 tons. By 1943, production reached over 200,000 tons annually. The United States eventually manufactured over 2 million tons of PSB during the war. Several variations emerged to meet different requirements. The original M7 specification became standard for bomber runways, using heavier gauge steel for maximum durability. The M8 variant used lighter gauge steel, suitable for fighter strips and taxiways where aircraft were lighter. The M9 consisted of square panels rather than long planks, designed for parking aprons and roads where the rectangular shape was more efficient. Each variant maintained the same interlocking principle, allowing different types to connect together at transition points. PSB's strategic value extended beyond its technical specifications. Because it was manufactured in the United States and shipped as finished products, quality control remained high. Unlike construction projects that depended on local materials and conditions, PSB provided consistent, predictable performance. Commanders planning amphibious operations could accurately calculate how many tons of matting they needed for a specific airfield, ship that quantity, and know with certainty that it would perform as required. While Marston mat solved the surface challenge, airfields still required foundations. PSB could distribute loads, but it needed to rest on something relatively stable and well-drained. Soft mud, loose sand, or waterlogged soil would cause even load-distributed matting to sink or shift. Traditional civil engineering called for foundations of crushed rock or gravel, compacted in layers. These materials simply didn't exist on most Pacific islands. The solution was coral, ubiquitous throughout the Pacific, and once engineers understood its properties, nearly ideal for rapid airfield construction. Coral reefs form from the calcium carbonate skeletons of countless coral polyps and other marine organisms deposited over centuries or millennia. Living coral reefs fringe most Pacific islands. Dead coral forms much of the islands themselves, ancient reefs uplifted by geological processes, or coral sand and rubble cemented together. The Pacific Theater offered an essentially unlimited supply of coral in various forms. Living reefs in shallow waters, dead coral formations above and below water, coral sand beaches, and coral rubble deposits. The key discovery was that crushed coral, properly processed and compacted, created excellent foundations. Coral's chemical composition, primarily calcium carbonate, gives it moderate hardness when dry. More importantly, coral's structure is naturally angular and irregular. When crushed into graded sizes, these angular fragments lock together under compaction, creating a stable matrix. Unlike rounded sand grains that slip past each other under load, angular coral fragments resist movement. Coral also possessed superior drainage characteristics. Its porous internal structure and the voids between compacted particles allowed water to percolate rapidly downward. This was crucial in the tropics, where sudden intense rainstorms could dump inches of rain in hours. Airfields built on coral foundations remained operational during and immediately after storms, while conventional soil-based runways would become quagmires. Engineers discovered that different coral sources had different properties. Reef coral, the dense, wave-resistant formations on outer reef edges, was harder and more durable than lagoon coral. However, lagoon coral was often easier to excavate and process. Coral sand, while readily available on beaches, required crushing to create the angular particles necessary for proper compaction. Dead coral formations above the waterline were usually ideal. Already dried, moderately hard, and accessible to heavy equipment. The Seabees developed systematic methods for coral exploitation. Site selection began with surveys to locate suitable coral deposits near the planned airfield. Geologists and engineers examined coral formations, testing hardness and structure. They preferred deposits that were accessible to bulldozers and close enough to minimize haul distances. Every mile saved in hauling coral to the runway site saved fuel and equipment wear. Extraction methods varied by coral type. Dense reef coral required heavy rippers, steel teeth mounted on bulldozers that could break up the formations. Operators learned to work systematically, breaking coral into chunks small enough to transport but large enough to avoid creating excessive dust. Coral sand deposits could be loaded directly but required crushing before use. Underwater coral required different techniques, sometimes explosives to break up formations, followed by draglines or clamshells to bring the material ashore. Crushing was essential. Raw coral chunks, even when compacted, left too many large voids and didn't achieve adequate density. Crushers reduced coral to specified gradations, typically a mixture of sizes from fine particles up to 2-3-inch fragments. This gradation was critical. Too uniform and the material wouldn't compact well, too much fine material and it became dust, too much large material and gaps remained between particles. The Seabees used various crusher types. Jaw crushers, where coral passed between two metal plates that moved together and apart, were most common. Portable units could be disassembled, shipped, and reassembled near work sites. Larger permanent installations used rotary crushers or impact mills. In emergencies, Seabees improvised, using captured Japanese equipment, modifying other machines, or even crushing small quantities by hand. Gradation control ensured quality. Screens sorted crushed coral into size ranges. Material that didn't pass through the required screen size returned to the crusher. Material that fell through too fine screens was set aside or used for other purposes. The goal was a well-graded mix where smaller particles filled voids between larger ones, maximizing density. Foundation construction followed systematic procedures. First, engineers cleared and graded the runway alignment, removing vegetation, topsoil, and any unsuitable material. If the natural ground was particularly soft, they sometimes excavated several feet down and backfilled with coral to create adequate bearing capacity. The cleared area was then shaped to proper drainage grades, typically a slight crown in the center of the runway with gradual slopes toward the edges. Coral placement occurred in lifts, layers typically 3 to 4 inches thick when loose, compacting to 2 to 3 inches. Dump trucks spread each lift across the runway width. Graders precisely leveled the material to specified elevations. Then came compaction, the critical step that transformed loose coral into a stable foundation. Compaction equipment included various rollers. Sheepsfoot rollers with protruding knobs that penetrated the lift and compacted from below upward worked well for initial passes. Smooth steel drum rollers provided final compaction and surface smoothing. Vibratory rollers, when available, significantly improved compaction efficiency. The number of passes required depended on coral properties, moisture content, and lift thickness, but typically ranged from 6 to 12 passes per lift. Moisture content affected compaction significantly. Slightly damp coral compacted better than completely dry material. The moisture helped particles move into optimal positions and acted as a temporary lubricant during compaction. However, too much moisture prevented proper compaction and created a soupy mess. Experienced operators learned to recognize optimal moisture by the coral's appearance and how it behaved under equipment. Quality control testing ensured adequate compaction. Engineers used penetrometers to measure soil resistance. Properly compacted coral showed high resistance to penetration. They also measured density, typically by digging test pits, weighing the excavated material, and calculating density per cubic foot. Specifications typically required coral foundations to achieve 95% of maximum density, as determined by laboratory testing. Multiple lifts built up the total foundation thickness. Specifications varied by aircraft type and expected traffic, but typical bomber runways required 12 to 18 inches of compacted coral. Each lift was placed, compacted, tested, and approved before the next lift went down. This layer-by-layer approach ensured uniform quality throughout the foundation depth. The final surface preparation was crucial. Before laying PSB, crews carefully graded the top lift to precise elevations. Any irregularities would cause PSB to rock or create gaps between the matting and foundation. A perfectly smooth, uniformly compacted surface ensured that aircraft loads transferred efficiently from the matting into the foundation. The Seabees coral and steel technique first proved itself at Guadalcanal in the Solomon Islands. When the 1st Marine Division landed on August 7, 1942, they found that Japanese forces had been constructing an airfield near Lunga Point. The partially completed facility, immediately renamed Henderson Field in honor of a Marine aviator killed at Midway, offered a ready-made runway alignment, but construction quality was minimal and the surface couldn't support heavy aircraft or sustained operations. The 6th Naval Construction Battalion arrived on September 1, 1942, joining remnants of the 1st Marine Engineer Battalion already working on the field. The situation was desperate. Japanese forces controlled much of Guadalcanal and subjected Henderson Field to regular artillery bombardment and almost nightly air raids. During the day, Japanese positions on nearby hills watched American activity. At night, Japanese warships sometimes bombarded the field from offshore. The Tokyo Express, fast destroyer runs bringing Japanese reinforcements, operated regularly down the slot between the Solomon Islands. Despite these conditions, the Seabees immediately began systematic airfield improvement. The 6th Battalion's commander, Commander Henry Jocelyn, assessed the situation and recognized that coral offered the solution to Henderson Field's mud problems. The battalion's equipment included bulldozers, graders, rollers, and critically, a rock crusher that had been shipped in pieces and required assembly. The Seabees first surveyed nearby coral deposits. Extensive formations existed along the coast and in the shallow waters off Lunga Point. They established extraction sites at multiple locations, minimizing haul distances to different parts of the runway. Work crews operated around Japanese shelling schedules. When shells started falling, everyone took cover. When the bombardment ended, work resumed. Coral extraction began with bulldozers fitted with ripper teeth breaking up formations. Initially, equipment wear was severe. Nobody had experience working coral, and operators learned through trial and error. Bulldozer blades dulled rapidly. Ripper teeth broke, but the Seabees adapted quickly, developing techniques to minimize equipment damage while maximizing coral extraction. The captured Japanese rock crusher, once assembled and made operational, provided crucial crushing capacity. Seabees fed coral chunks into the crusher, which reduced them to usable gradations. When the crusher broke down, a frequent occurrence with captured equipment, mechanics worked overnight to repair it. Spare parts came from cannibalizing other equipment or fabricating replacements in the battalion's machine shop. Coral hauling proceeded continuously. Dump trucks ran shuttle routes from extraction sites to the runway, often driving through mud holes and shell craters. When trucks bogged down, bulldozers pulled them out. When fuel ran short, the Seabees prioritized the haulers. The coral had to keep flowing to maintain construction momentum. Foundation construction followed the systematic lift-by-lift procedure, though compressed by combat conditions. Graders spread coral as trucks dumped it. Rollers followed immediately behind, compacting each lift. Quality control was abbreviated. Engineers checked obvious problems but couldn't perform comprehensive testing while under fire. The goal was good enough for operations rather than peacetime perfection. PSB installation began in late September as the foundation reached completion. The 6th Battalion had brought limited quantities of matting, which they laid on the most used portions of the runway. The interlocking planks went down quickly, crews became proficient at the hooking process, and installation proceeded despite occasional interruptions for air raid warnings. The transformation was dramatic. Before the Seabees work, Henderson Field was barely functional during dry weather and completely unusable after rains. Aircraft bogged down taxiing. Takeoffs required maximum power runs through mud. After completion of the coral foundation and PSB surface, the field operated in all weather. Heavy rains that previously would have grounded all aircraft now caused only minor puddling that drained within hours. Henderson Field's operational impact was immediate and decisive. Marine, Navy, and Army Air Force aircraft operating from the field attacked Japanese ships, bombed enemy positions throughout the Solomons, and provided close air support for ground forces. The Cactus Air Force, the mixed collection of units based at Henderson, achieved air superiority over Guadalcanal despite being heavily outnumbered. Japanese reinforcement convoys suffered devastating losses. The Tokyo Express could only operate at night when American aircraft couldn't attack. The Seabees continued improving Henderson Field throughout the Guadalcanal campaign. They extended the runway from its initial 3,800 feet to over 6,000 feet, allowing operation of larger bombers. They constructed Fighter Strip 1 and Fighter Strip 2 as auxiliary runways, dispersing aircraft to reduce vulnerability to air attacks. They built taxiways, parking revetments, fuel storage facilities, and ammunition dumps. All followed the same Coral NPSB technique. Combat casualties affected the Seabees as much as combat units. Japanese artillery and air attacks killed and wounded construction workers regularly. Seabees learned to work with weapons nearby. The battalion's defensive positions surrounded key facilities. Men operating bulldozers kept rifles within reach. Coral crushing continued even during air raids unless bombs actually fell on the crusher site. By the time American forces completed Guadalcanal's capture in February 1943, Henderson Field had evolved from a rudimentary Japanese airstrip into a major airbase complex. The Seabees had constructed over 10,000 feet of runways, miles of taxiways, and extensive support facilities. They had quarried and processed hundreds of thousands of tons of coral, and they had validated the Coral NPSB technique under the worst possible conditions. If it worked at Guadalcanal while under fire and short of supplies, it would work anywhere. The success at Henderson Field led to rapid systematization of coral-based airfield construction. Throughout late 1942 and early 1943, the Navy's Civil Engineer Corps developed detailed specifications, standardized procedures, and training programs. Every Seabee battalion deploying to the Pacific received instruction in coral identification, extraction, processing, and foundation construction. Engineering manuals codified the techniques. Airfield construction in the Pacific became required reading for Seabee officers. The manual covered site selection, coral surveys, equipment requirements, extraction methods, crushing specifications, foundation construction procedures, PSB installation, and quality control testing. It included photographs, diagrams, and step-by-step instructions. Later editions incorporated lessons learned from ongoing operations. Training facilities in the United States prepared Seabee battalions for Pacific deployment. At Camp Peary in Virginia, Camp Endicott in Rhode Island, and Port Hueneme in California, construction battalions practiced airfield construction using techniques as similar as possible to Pacific conditions. While actual coral wasn't available, crushed limestone provided similar characteristics. Battalions practiced the complete sequence from site clearing through PSB installation. Equipment standardization proceeded simultaneously. The Navy specified standard equipment sets for Seabee battalions, sized according to expected missions. A typical battalion assigned to airfield construction received bulldozers with ripper attachments, motor graders, sheepsfoot and smooth drum rollers, portable crushers, dump trucks, water trucks, and surveying equipment. Spare parts inventories were prepackaged to support expected maintenance requirements. Portable crusher design improved significantly. Early models were often unreliable and difficult to transport. By 1943, manufacturers produced standardized portable crushers that could be disassembled into components light enough for ship or truck transport, then reassembled in the field within days. Capacity increased. Later models could process 100 tons per hour or more, significantly exceeding earlier equipment. PSB handling equipment evolved as well. Initial installations were entirely manual. Crews carried planks to position, hooked them together, then moved to the next one. This was labor-intensive and slow. Engineers developed specialized trailers that could transport stacks of PSB and deploy them directly onto the runway. Some units fabricated simple mechanical assists, wooden ramps or rollers that made positioning planks easier. Quality control procedures became more sophisticated. Engineers developed field-expedient testing methods that provided reliable results without laboratory equipment. Sand cone density tests, dynamic cone penetrometers, and visual classification systems allowed field engineers to assess compaction quality quickly. Specifications included both minimum performance standards and testing frequencies, typically one test per 1,000 square feet of runway surface. Drainage design received increased attention. Early airfields sometimes experienced problems with water accumulation despite coral's good drainage properties. Engineers learned to incorporate positive drainage features. Crowned runway surfaces that shed water to the edges, ditches along runway sides to collect runoff, and proper grading of surrounding areas to prevent water flowing onto the runway. On low-lying atolls barely above sea level, they sometimes constructed entire airfields on raised platforms, requiring enormous quantities of fill material but ensuring drainage. The Navy also developed specifications for different airfield classes. Class A fields, designed for heavy bomber operations, required the most stringent specifications, thicker foundations, higher compaction requirements, and full PSB coverage. Class B fields for medium bombers and fighters had reduced requirements. Class C fields, emergency strips for fighters only, could be constructed with minimal foundations and partial or no PSB coverage. This classification system allowed commanders to match construction effort to operational requirements. The airfield construction at Munda, New Georgia, demonstrated how refined techniques and concentrated resources could achieve remarkable speed. American forces captured Munda on August 5, 1943, after weeks of difficult fighting through jungle terrain. Japanese defenders had constructed a significant airfield before American invasion, but bombardment and combat had heavily damaged it. The strategic situation demanded immediate restoration. Munda would support the next phase of the Solomons campaign, the assault on Bougainville. The Navy committed 3 complete Seabee battalions to Munda simultaneously, the 24th, 73rd, and 77th Naval Construction Battalions, totaling over 3,000 men. This concentration of construction power was unprecedented. Each battalion brought full equipment sets. The invasion convoy included dedicated cargo ships carrying PSB, fuel, spare parts, and construction supplies. Work began literally within hours of Munda's capture. Advanced parties from all 3 battalions went ashore on August 5 and 6 while fighting still continued in outlying areas. They conducted rapid reconnaissance, located coral deposits, and identified equipment landing sites. By August 7, bulldozers were clearing the existing runway alignment and beginning coral extraction. The 3 battalions divided responsibilities. The 24th Battalion took primary responsibility for the main runway, working from south to north. The 73rd Battalion handled the northern section and began developing a parallel taxiway. The 77th Battalion established coral processing facilities and managed material hauling. This division of labor prevented units from interfering with each other while maintaining construction momentum. Coral extraction occurred at multiple sites simultaneously. Survey teams had identified extensive coral formations both along the coast and inland where ancient uplifted reefs existed. The 77th Battalion established 3 separate quarry sites, each with dedicated equipment. Bulldozers with rippers worked continuously, breaking up coral formations. Loaders moved the chunks to crusher sites. Crushing operations ran 24 hours daily. The Navy had shipped multiple portable crushers to Munda, recognizing that single crusher operations created bottlenecks. 3 crusher installations, each capable of processing 7,500 tons hourly, operated simultaneously. Maintenance crews worked between shifts to keep crushers operational. When parts failed, welders fabricated replacements overnight. The scale of the hauling operation was impressive. Dozens of dump trucks shuttled continuously between quarries and the runway. Haul roads, themselves constructed with coral, connected all work sites. Traffic control became necessary. Trucks ran in one-way loops to maximize efficiency. Fuel trucks refilled equipment on site to minimize downtime. Foundation construction proceeded section by section. As graders finished shaping one runway section, the compaction train moved in, first the sheep's-foot rollers, then the smooth drums. While rollers compacted one section, other equipment prepared the next. The construction resembled an assembly line, with each work element following smoothly behind the previous one. PSB installation began before the entire runway foundation was complete. The 24th Battalion started laying matting on completed sections at the runway's south end, while foundation work continued northward. This parallel processing dramatically reduced overall construction time. Crews became highly proficient at PSB installation. They developed techniques for rapid plank handling and established rhythms that allowed swift progress. Floodlights enabled night operations. Generator sets provided power for lighting the active construction areas. While night work was less efficient than daylight operations, visibility was limited, and equipment operators worked more cautiously, it still contributed significantly to overall progress. The 24-hour work schedule meant construction advanced continuously. The results were extraordinary. By August 14, 1943, just 9 days after capture, Munda had a functional 4,000-foot runway. Fighter aircraft began operating immediately, providing air cover for ground forces still mopping up Japanese resistance elsewhere on New Georgia. By August 27, the runway extended to 6,000 feet, and bomber operations commenced. Within 2 months, Munda had evolved into a complete airbase complex with multiple runways, extensive taxiways and parking areas, fuel storage for tens of thousands of gallons, ammunition magazines, and facilities for over 200 aircraft and thousands of personnel. Munda proved that Coral and PSB techniques could deliver operational airfields with unprecedented speed when adequate resources were committed. The 9-day timeline from capture to initial operations set a benchmark. Later projects would sometimes match or even exceed this pace, but Munda established that rapid airfield construction was not just theoretically possible, but practically achievable. As American forces advanced through the Gilbert, Marshall, and Mariana Islands in 1943–1945, Seabee airfield construction evolved to support progressively larger operations. The Central Pacific Islands were generally atolls, rings of coral surrounding lagoons, with land areas barely above sea level. These presented different challenges than the volcanic islands of the Solomons. Tarawa Atoll and the Gilberts saw some of the war's most intense fighting when Marines assaulted Batio Island in November 1943. The 2nd Naval Construction Battalion landed on D+2 days after the initial assault, while fighting still raged. Japanese defenders held fortified positions, and occasional sniper fire and counterattacks continued for days. The Seabees began work immediately despite these conditions. Batio presented unique challenges. The island was tiny, less than 300 acres and barely 5 feet above sea level at its highest point. The existing Japanese airfield occupied much of the island's length, but the battle had churned the island into a moonscape. Bomb craters, destroyed fortifications, wrecked equipment, and debris covered everything. Before airfield construction could even begin, massive cleanup was necessary. The Seabees organized systematic debris removal. Bulldozers pushed destroyed Japanese aircraft, vehicles, and fortifications into piles. Salvage teams sorted through wreckage, recovering useful materials and clearing others. The grim task of recovering remains, both American and Japanese, preceded construction in many areas. Only after clearing could airfield work proceed. Coral was readily available but required different extraction approaches than on larger islands. Batio's land area offered limited coral sources, so the Seabees turned to the lagoon. They used underwater demolition techniques, setting charges to break up coral heads in the shallow lagoon waters. Clamshells and draglines brought the coral ashore. Other crews collected coral rubble from beaches and nearby islets. Working on such a small island created logistical complexities. Everything was crowded: combat units, supply dumps, command posts, medical facilities, and construction operations all competed for limited space. Equipment and materials arrived continuously by landing craft, which had to wait their turn to beach and unload. Supplies piled up on beaches until they could be moved to work sites. Traffic control became critical. Vehicles could barely maneuver on the narrow island. Despite these challenges, the 2nd Battalion completed a usable fighter strip within a week. The foundation used coral from the lagoon and existing land, processed through portable crushers set up on the beach. PSB provided the surface. The first fighters landed on November 29, 1943, 9 days after the initial assault. They immediately began operations, providing air cover for subsequent operations in the Marshall Islands. The Marshall Islands campaign in early 1944 involved multiple simultaneous airfield construction projects across dispersed atolls. At Majuro, Kwajalein, and Eniwetok, separate Seabee battalions worked concurrently. The Navy had refined its deployment procedures. Each assault convoy included dedicated construction support shipping with preloaded equipment and materials. Eniwetok Atoll demonstrated the Seabees' capability for distributed operations. The atoll contained multiple islands, and the Navy planned airfields on 3, Njebai, Eniwetok, and Perry Islands. Different battalions took responsibility for each island, working independently but coordinating through the overall command structure. At Njebai, the 110th Naval Construction Battalion began work on February 18, 1944, the day after the island's capture. Njebai offered excellent coral sources. The island sat atop extensive reef formations. The 110th established quarries at both ends of the island and set up a large crusher installation in the center. They constructed a 6,000-foot bomber runway and a complete base complex within 6 weeks. On Eniwetok Island, the 106th Battalion built a similar facility. Perry Island received a fighter strip from the 121st Battalion. The three islands' airfields operated as an integrated system, providing fighters, bombers, and reconnaissance aircraft. The coordinated effort demonstrated the Seabees' organizational maturity, independent battalions working separate projects that complemented each other strategically. The Marianas Campaign, Saipan, Tinian, and Guam captured in summer 1944, represented the ultimate application of Seabee airfield construction techniques. These islands would host B-29 Superfortress strategic bomber bases for operations against Japan's home islands. The requirements far exceeded any previous project. B-29s were the war's largest bombers, with maximum takeoff weights approaching 140,000 pounds. They required runways exceeding 8,500 feet long with surfaces capable of handling extreme wheel loads. The Marianas bases would host hundreds of B-29s, requiring extensive parking areas, maintenance facilities, fuel storage for millions of gallons, and bomb storage for thousands of tons of ordnance. The construction effort would dwarf anything previously attempted in the Pacific. Tinian became the largest airfield complex. The island offered several advantages. It was relatively flat, possessed good coral sources, and provided sufficient area for multiple parallel runways. The Navy assigned the 6th, 38th, 121st, and 135th Naval Construction Battalions to Tinian, along with elements from other battalions for specialized work. Planning preceded execution. Engineers surveyed the entire island before combat ended, identifying optimal runway alignments, coral quarry sites, and facility locations. They planned a 4-runway complex with 2 parallel 8,500-foot runways and 2 more crossing at angles. Supporting facilities would include hardstands for over 200 bombers, fuel storage for 10 million gallons, and 40 bomb-loading pits. Coral extraction occurred on an unprecedented scale. The Seabees established quarries at multiple sites across Tinian. At peak operations, dozens of bulldozers worked simultaneously, breaking up coral formations. The volume was staggering. Engineers calculated that Tinian's runways alone required over 1 million cubic yards of coral for foundations. Crushing capacity had to match extraction rates. The Navy shipped multiple large crusher installations to Tinian, including semi-permanent facilities capable of processing hundreds of tons hourly. Crusher operations ran continuously. Maintenance became a dedicated function. Teams worked around the clock keeping equipment operational. The hauling effort involved hundreds of trucks. At peak activity, over 200 dump trucks ran continuous shuttle routes between quarries and construction sites. Haul roads crisscrossed the island. Traffic control used one-way routing systems and designated passing areas. The Navy even brought in traffic control personnel from military police units to manage vehicle flow. Foundation construction proceeded systematically. Tinian's runways required foundations 18 inches thick, the deepest specifications used in the Pacific. The Seabees placed, spread, and compacted coral in 6 separate lifts. The volume of material handled was enormous. Each runway required approximately 150,000 tons of coral for its foundation alone. PSB installation consumed months. A single 8,500-foot runway required approximately 15,000 tons of matting. 4 runways meant 60,000 tons total, equivalent to a Liberty ship's cargo capacity. The matting arrived continuously throughout construction, and installation crews worked section by section as foundations reached completion. Quality control was rigorous. With B-29 operations planned, any foundation or surface defects could prove catastrophic. Engineers tested compaction density extensively, requiring 95% of maximum theoretical density throughout the foundation depth. Surface smoothness specifications were strict. Variations exceeding 1 inch over 10 feet were unacceptable. Inspection teams surveyed completed sections with precision equipment before approving them for PSB installation. The first Tinian runway became operational in December 1944. By February 1945, the entire 4-runway complex was complete. At its peak, Tinian hosted over 200 B-29s from the 313th, 314th, 509th, and 58th Bombardment Wings. The bases launched hundreds of sorties daily against Japanese cities and industrial targets. The atomic bomb missions against Hiroshima and Nagasaki in August 1945 departed from Tinian's runways, built by Seabees using crushed coral and steel matting. Saipan and Guam hosted similar though slightly smaller complexes. Saipan's Isley Field, renamed Isley Field for Commander Robert Isley, killed in combat, received B-29s from the 73rd Bombardment Wing. Guam's North Field and Northwest Field housed additional bomber groups. Together, the Marianas bases represented the Pacific War's largest concentration of air power, made possible by Seabee engineering. Iwo Jima presented the most challenging airfield construction environment of the entire Pacific War. The island offered significant strategic value. Positioned midway between the Marianas and Japan, it could host fighters to escort B-29s and provide emergency landing facilities for damaged bombers returning from Japan. But capturing and developing Iwo Jima would prove extraordinarily costly. Japanese forces had constructed 3 airfields on Iwo Jima before American invasion. Chidori Field in the south, Motuama No. 1, captured early and renamed South Field, and Motuama No. 2 in the north. The February 1945 invasion aimed to capture these fields and develop them for American use. The 31st, 62nd, and 133rd Naval Construction Battalions landed with assault forces on February 19, 1945. Unlike typical Pacific invasions, where Japanese forces defended beaches, then withdrew inland, Iwo Jima's defenders had constructed extensive underground fortifications throughout the island. They intended to inflict maximum casualties through prolonged resistance. This meant the Seabees worked under fire throughout the battle. Japanese positions on Mount Suribachi overlooked South Field. Artillery, mortars, and machine guns targeted the airfield continuously. As Marines advanced northward, construction crews followed, but Japanese defenders emerged from hidden fortifications to attack from behind American lines. Snipers were everywhere. The 31st Battalion began work on South Field on D-Day itself, February 19. While Marines fought to expand the beachhead, Seabees used bulldozers to clear wrecked Japanese aircraft and repair bomb damage to the existing runway. Enemy fire was intense. Bulldozer operators worked with rifles propped beside their seats. Multiple Seabees were killed or wounded while operating equipment. Iwo Jima's volcanic soil presented unique problems. The island consisted primarily of volcanic ash and cinders rather than coral. This material had virtually no bearing capacity when loose and turned to a sticky mess when wet. Traditional coral-based foundation techniques wouldn't work. Suitable coral simply didn't exist in sufficient quantities. The Seabees improvised solutions. They excavated volcanic ash from runway areas down to harder material, sometimes several feet deep. They filled these excavations with any suitable material they could find. Crushed rock from volcanic formations, coral scraped from beaches, even compacted ash mixed with cement when available. They used exponentially more PSB than on coral-based fields, essentially creating runways where the matting carried most of the load with minimal foundation support. Despite the conditions, South Field became operational on February 26, just 7 days after invasion. The runway was rough, the surface irregular, and the facilities minimal, but it was functional. The first aircraft to use it was a damaged B-29 that made an emergency landing, exactly the mission for which Iwo Jima was captured. Throughout March and April, while fighting continued, damaged B-29s made emergency landings at Iwo Jima regularly. Some aircraft that landed were so badly damaged they never flew again, but their crews survived. Casualties among Seabee personnel were severe. Working under continuous fire for weeks, all 3 construction battalions suffered killed and wounded. Some were hit while operating equipment. Others died when enemy positions previously thought cleared suddenly erupted with fire. Seabees earned numerous decorations, including Silver Stars and Bronze Stars, for actions during the Iwo Jima operation. By the time the island was declared secure on March 26, the Seabees had repaired South Field, extended its runway to over 7,000 feet, and begun work on the northern airfields. Eventually, Iwo Jima hosted 3 operational airstrips supporting fighters that escorted B-29s to Japan and emergency landing facilities that saved thousands of American airmen. The cost was high, but the strategic value justified it. Over 2,400 B-29s made emergency landings at Iwo Jima during the last months of the war. Okinawa, captured in a brutal campaign from April through June 1945, would become the final staging point for the planned invasion of Japan. The island's size and location made it ideal for massive air, naval, and ground forces buildup. Seabee construction at Okinawa reached scales exceeding even the Marianas. Multiple airfield sites were developed simultaneously. Yontan Airfield and Kadena Airfield, both captured early in the campaign, received immediate attention. The 88th, 96th, and 804th Naval Construction Battalions began work while combat units fought for control of southern Okinawa. Both fields had been built by the Japanese, but required extensive modification for heavy American aircraft. The Seabees quarried coral from multiple sites across northern Okinawa. They constructed new haul roads, established crusher installations, and began systematic runway reconstruction. Unlike Iwo Jima, Okinawa offered excellent coral sources, and construction proceeded using the refined techniques developed over 3 years of Pacific operations. The scale was massive. Plans called for runways capable of handling not just B-29s, but the even larger B-32 and potentially B-36 bombers then under development. Engineers specified 18-inch coral foundations compacted to maximum density. PSB coverage extended across entire runways, taxiways, and parking areas totaling millions of square feet. Kamikaze attacks complicated construction. Japanese suicide aircraft targeted American ships offshore but sometimes struck land targets, including airfields under construction. The Seabees worked under air raid alerts regularly. When raids occurred, they took cover. When the all-clear sounded, they resumed work. By June 1945, Okinawa hosted multiple operational airfields. Yontan and Kadena became major bomber bases. Additional fields supported fighters, reconnaissance aircraft, and transports. The island evolved into a massive staging base for Operation Olympic, the planned invasion of Kyushu scheduled for November 1945. The atomic bombings of Hiroshima and Nagasaki and Japan's subsequent surrender meant Olympic never occurred, but Okinawa's airfields demonstrated the Seabees' capability to construct facilities for any scale of operations. While airfields received priority, Seabees constructed comprehensive infrastructure throughout the Pacific using the same coral and steel techniques. Roads connected ports to airfields, supply depots, command centers, and defensive positions. Without proper roads, military traffic would bog down in tropical mud. The Seabees applied airfield engineering principles to road construction. Clear unsuitable soil, lay compacted coral foundations, and surface with PSB or compacted coral depending on expected traffic. Parking hardstands proliferated around every airfield. Aircraft couldn't park on grass, they'd sink into soft ground. Each hardstand required a coral foundation and PSB surface capable of supporting a fully loaded bomber plus support vehicles. Large bases had hundreds of hardstands, each essentially a miniature runway section. Port facilities required extensive coral work. Few Pacific islands had deep-water harbors or piers. The Seabees built causeways extending from beaches into deeper water where LSDs and cargo ships could unload. These causeways used coral fill contained by timber cribs or coral boulder breakwaters. They constructed ammunition piers using similar techniques, designing them to contain explosions if accidental detonation occurred, a grim necessity given the quantities of explosives handled. Fuel storage facilities consumed significant construction effort. Bases required millions of gallons of aviation gasoline, diesel for equipment, and other petroleum products. The Seabees excavated tank farms, built containment berms using coral, and constructed distribution systems. Some tank farms held over 10 million gallons stored in multiple tanks, each requiring proper foundations and safety features. Ammunition storage bunkers used coral extensively. Magazines were typically constructed by excavating into hillsides or building earthen berms around reinforced structures. The Seabees used coral fill for these berms, compacting it to provide blast protection. Ammunition storage areas sprawled across acres, with separate bunkers for different ordnance types. Living facilities for tens of thousands of personnel required infrastructure. The Seabees constructed tent cities with coral roads, drainage systems, freshwater distribution, and sanitation facilities. They built mess halls, hospitals, recreation areas, and command centers. Coral surfacing extended throughout these facilities, keeping areas passable during tropical downpours. Airfield maintenance was continuous. Aircraft operations caused inevitable wear on both PSB and coral foundations. Tires wore grooves in matting. Heavy landings damaged planks. Repeated traffic compacted foundations unevenly. Tropical weather caused gradual deterioration. The Seabees maintained permanent detachments at major bases for ongoing maintenance. Damaged PSB planks were unhooked and replaced. Worn sections underwent complete renewal, removing old matting, reworking the foundation, and installing new planks. Areas showing foundation settlement received additional coral, recompaction, or both. Drainage maintenance was critical. Ditches along runways required regular cleaning to maintain water flow. Culverts clogged with debris or coral dust needed clearing. Grading required constant attention. Tropical rains eroded surfaces, and heavy equipment traffic created ruts. Maintenance crews continuously patrolled facilities, identifying and correcting problems before they affected operations. Equipment maintenance consumed enormous effort. The hostile environment accelerated wear. Coral dust infiltrated engines, hydraulic systems, and bearings. Salt air corroded metal components. Tropical heat caused lubrication breakdown. Bulldozers, graders, and other equipment required servicing far more frequently than in temperate climates. The Seabees established maintenance facilities at every major base. These included machine shops with lathes, milling machines, and welding equipment. Mechanics performed regular preventive maintenance and repaired damaged equipment. When parts weren't available through supply chains, they fabricated replacements. This ability to maintain and repair equipment in the field was crucial. Waiting for factory repairs would have crippled construction operations. Spare parts supply challenged logistics systems. Maintaining hundreds of pieces of heavy equipment across thousands of miles of ocean required extensive parts inventories. The Navy prepositioned parts at advanced bases and shipped high-demand items continuously. Despite these efforts, shortages occurred regularly, and mechanics' ability to improvise repairs or fabricate parts proved essential. Throughout the Pacific Campaign, Seabees continuously innovated and adapted. They developed coral ripper tooth designs that maximized extraction while minimizing wear. They experimented with different crusher configurations to optimize throughput and reduce maintenance. They refined compaction techniques based on coral properties at specific locations. Some battalions created specialized equipment. Fabrication shops built coral spreaders from truck frames and steel plate, allowing more uniform material distribution. Others developed mechanical mat laying assists, reducing the manual labor required for PSB installation. These innovations spread through informal networks as battalions rotated between assignments and personnel shared experiences. Coral mixing experiments improved foundation quality. The Seabees discovered that blending coral from different sources sometimes produced superior results. Mixing harder reef coral with softer lagoon coral created gradations that compacted better than either type alone. Adding coral sand to crushed material filled small voids, increasing density. Stabilization techniques evolved for special applications. When coral alone proved insufficient, the Seabees experimented with additives. Cement mixed with coral created a stabilized base with higher strength. Oil or bitumen mixed with coral improved water resistance. These techniques were expensive and labor-intensive, but valuable for critical applications like ammunition loading areas where extra durability justified the cost. Alternative foundation materials were developed when coral was scarce. On volcanic islands, the Seabees sometimes used crushed volcanic rock, though this required different processing and compaction procedures. On some atolls, they dredged calcareous sand from lagoon bottoms, crushed it to create angular particles, then compacted it in thick layers. These alternatives never matched coral's performance but provided acceptable solutions when necessary. The Seabees represented a unique military organization. Unlike traditional combat units recruited from the general population and trained for warfare, construction battalions actively recruited men with civilian construction experience. The Navy sought carpenters, heavy equipment operators, truck drivers, mechanics, electricians, welders, surveyors, engineers, and other skilled tradesmen. This produced units where many personnel possessed directly applicable skills before their first day of military training. Recruitment standards reflected these priorities. The Seabees accepted men older than typical enlistment ages, Many members were in their 30s or 40s, with families and established careers. They enlisted or received direct commissions because they possessed critical skills. A master carpenter might serve as a petty officer. An experienced civil engineer could receive a commission as a lieutenant or higher based on civilian qualifications. This older, more experienced demographic affected unit culture. Seabee battalions operated with less formality than typical military units. Rank still mattered, but civilian expertise often carried equal or greater weight. An enlisted heavy equipment operator with 20 years of civilian experience might direct bulldozer operations while officers handled logistics and coordination. This practical approach maximized efficiency. Training combined military basics with technical skills. Seabee boot camp covered military discipline, physical conditioning, weapons training, and basic military knowledge. But unlike infantry training that emphasized combat skills, Seabee training focused on construction. Recruits with civilian experience received refresher training and introduction to military equipment. Those without construction backgrounds received intensive technical training in specific trades. Construction battalion structure reflected civilian construction organization more than traditional military hierarchy. A typical battalion included specialized companies. Company A might focus on earthmoving and foundations, Company B on vertical construction, Company C on utilities and infrastructure, and Company D on maintenance and support. Within companies, smaller units specialized further: concrete crews, steel workers, equipment operators, carpenters, electricians. This structure allowed the battalion to tackle complex projects by assigning the right specialists to each task. Officers came from diverse backgrounds. Some held civilian engineering degrees, civil, mechanical, or industrial engineering. Others had managed large construction projects or owned construction companies. The Navy offered direct commissions to qualified civilians, bringing them in as lieutenants, lieutenant commanders, or even commanders based on experience. These officer engineers brought professional competence that proved invaluable in the complex construction projects the Pacific demanded. Yet the Seabees also trained for combat. The motto, "We build, we fight," wasn't just rhetoric. Every Seabee received weapons training and combat instruction. Battalions included dedicated defensive platoons, but all personnel could man positions during attacks. This proved necessary repeatedly. Japanese forces specifically targeted construction operations, understanding that preventing airfield completion denied Americans air superiority. Combat casualties affected Seabee battalions significantly. At Guadalcanal, Iwo Jima, Okinawa, and numerous other locations, Seabees died or were wounded while working or defending their positions. They earned Purple Hearts, Bronze Stars, Silver Stars, and other decorations. Several Seabees received the Navy Cross for extraordinary heroism. Their dual role, construction workers and combat troops, meant they faced dangers from both enemy action and the inherent hazards of heavy construction. The Seabees' Pacific achievements influenced post-war military and civilian engineering profoundly. Pier steel planking remained in service for decades. American forces used PSB in Korea, constructing and repairing airfields under combat conditions using techniques perfected in the Pacific. In Vietnam, PSB surfaced airfields, helicopter pads, and roads throughout South Vietnam. Later conflicts saw continued PSB use, with improved materials but the same basic concept. Modern military airfield matting systems evolved directly from PSB. The Air Force's AM-2 matting, introduced in the 1960s, used aluminum instead of steel, reducing weight while maintaining strength. Current systems employ composite materials offering further improvements, but all maintain the core PSB principles. Interlocking panels that distribute loads can be rapidly deployed without special equipment and function over minimal foundations. Coral construction techniques influenced tropical engineering worldwide. After the war, engineers working on Pacific Island development projects adopted Seabee methods. Civilian airports throughout the Pacific used coral-based foundations. Roads, ports, and other infrastructure incorporated lessons learned during wartime construction. The techniques spread beyond the Pacific. Engineers in the Caribbean, Indian Ocean, and other tropical regions recognized coral's advantages and adapted Pacific construction methods. The rapid airfield construction concept influenced Cold War military planning. NATO developed procedures for rapid runway repair assuming conventional or nuclear strikes. These procedures incorporated PSB or similar matting, recognizing that quickly restoring airfield operations could be decisive. The ability to construct or repair airfields rapidly became a core military engineering capability, with roots in Seabee Pacific experience. Educational institutions studied Seabee achievements. Engineering schools incorporated Pacific airfield construction as case studies in field engineering, materials science, and construction management. The combination of material innovation, systematic procedures, and organizational efficiency provided valuable lessons for engineering students. Some universities developed entire courses examining World War II military construction. The Seabees themselves became a permanent naval organization. Unlike many wartime units that disbanded after 1945, the construction battalions continued as an active component of the Navy. They participated in Korea, Vietnam, and later conflicts. They conducted peacetime construction projects worldwide. The Seabees' World War II legacy established their permanent value to American military capability. The scale of Seabee airfield construction in the Pacific is difficult to comprehend. Over 400 airfields were constructed or significantly improved during the war. These ranged from small fighter strips a few thousand feet long to massive bomber complexes with multiple runways exceeding 8,000 feet each. Total PSB production exceeded 2 million tons, roughly equivalent to 30 million individual planks. If laid end-to-end, this would extend over 57,000 miles. The steel required to produce this matting came from mills across America, representing a significant allocation of wartime steel production. Coral processing reached extraordinary volumes. Estimates suggest Seabees quarried, crushed, and compacted over 100 million tons of coral during the Pacific Campaign. This material was extracted from reefs, beaches, and underwater formations across thousands of islands. The equipment hours required: bulldozers, crushers, trucks, and compactors operating continuously for years, represents one of history's largest construction efforts. Individual airfield statistics illustrate the scale. Tinian's 4-runway complex required approximately 2 million cubic yards of coral for foundations alone, equivalent to a pyramid 500 feet on each side and 200 feet tall. The runways consumed 60,000 tons of PSB, covering over 3 million square feet. Supporting facilities included parking for over 200 aircraft, fuel storage exceeding 10 million gallons, and infrastructure for over 20,000 personnel. The manpower involved was substantial. At peak strength in 1945, the Navy's construction battalions numbered over 325,000 men in 151 battalions. Not all served in the Pacific, some deployed to Europe, the Mediterranean, and other theaters. But the vast majority operated in the Pacific, where airfield construction dominated their missions. Equipment inventories were massive. A typical battalion assigned to major airfield construction included approximately 10-15 bulldozers, 5-8 motor graders, 4-6 rollers, 2-3 portable crushers, 50-75 dump trucks, and numerous support vehicles. Multiply this across over 100 battalions operating simultaneously in the Pacific, and the total equipment inventory reached thousands of major machines plus tens of thousands of trucks and support vehicles. Fuel consumption was staggering. Heavy equipment operating continuously consumed enormous quantities. A single bulldozer working 12-hour shifts burned approximately 50-75 gallons of diesel daily. With hundreds of bulldozers operating across the Pacific, daily fuel consumption for construction alone reached tens of thousands of gallons. This competed with combat operations for limited shipping capacity. The economic value of Seabee construction is difficult to calculate. Estimates suggest that airfield construction alone represented an investment exceeding $1 billion in 1940s dollars, equivalent to over $15 billion today. This doesn't include roads, ports, facilities, and other infrastructure. The Seabees represented one of the war's largest industrial efforts, comparable to shipbuilding programs or aircraft production. The Seabees' achievement in building Pacific airstrips with pierced steel planking and coral represents military engineering at its most innovative and decisive. They transformed a critical logistical challenge, how to construct airfields capable of supporting heavy aircraft on remote tropical islands lacking conventional construction materials, into a decisive advantage that enabled American victory. The combination was elegant in its practicality. Industrially produced steel matting that could be shipped efficiently and deployed rapidly, paired with a locally available material that, properly processed, created excellent foundations. Neither element alone would have sufficed. PSB without adequate foundations would have sunk into soft ground. Coral foundations without proper surfacing would have deteriorated under aircraft traffic and tropical weather. Together, they created a construction system that could be replicated across an entire theater of war while maintaining quality and achieving unprecedented speed. The strategic impact was profound. Island hopping depended on rapidly establishing air superiority from newly captured bases. Without the ability to construct operational airfields within days or weeks of an island's capture, the entire Pacific strategy would have been impossible. Conventional construction methods requiring months per base would have allowed Japanese forces time to reinforce subsequent objectives, potentially stalling the American advance indefinitely. The human element deserves recognition. The Seabees, older, experienced tradesmen who brought civilian expertise to military service, worked under conditions ranging from difficult to deadly. They built airfields while under fire, suffered casualties from enemy action and construction accidents, and maintained operations despite equipment shortages, supply problems, and tropical diseases. Their combination of professional competence and military determination made the engineering achievements possible. The legacy endures. Modern rapid runway systems trace their conceptual origins directly to PSP. Military engineering doctrine still emphasizes the principles the Seabees demonstrated: speed, adaptability, resourcefulness, and the ability to leverage both industrial capability and local materials. The coral construction techniques influenced tropical engineering worldwide, spreading far beyond their military origins. In the final analysis, the Seabees' coral and steel airfields formed the literal foundation of American Pacific victory. They enabled the air campaigns that isolated Japanese garrisons, supported amphibious operations, and ultimately brought strategic bombing to Japan's home islands. The engineering innovation, organizational efficiency, and human dedication that built those runways proved as decisive as any battle or campaign. The Seabees didn't just build airfields. They built victory, one coral-laden dump truck and one interlocking steel plank at a time.